most everybody. So Joaquin is just arrived from Japan. He did his PhD in Durham, right?
Mm-hmm.
And then he went to Japan.
Yeah,
and then he's here starting a postdoc with us so he's going to tell us about, I mean, the first talk, it's very good. He just arrived, so it's very nice that he was able to get over his jet lag and give us a talk about his work in the HSC, I guess, right?
Yes.
All right, thank you.
Thank you. Yes, as Raul said, I just arrived, so didn't have time to change my affiliations actually in the title. But yeah, this is what I'm going to talk today. Job I did during my postdoc in IPMU in Tokyo. But yeah, it has extensions to things I want to do in the future, including here. That's why I have this picture of LSSD. So yeah, the title is related to this work I did in biostatistics, applied mainly to stage 4 surveys. So yeah, this is work thinking for the future, but as I'm gonna mention, we already did some testing with the HSC data, which is, as you may know, a survey managed by Japan mainly. So that's the purpose of how these two different surveys are linked. So to start, I'm just gonna show an introductory cosmology slide that basically put in the context of why this work is important. So to start, we have these observations of cosmological sources. One is the CMB that's in the background, and this start from, as you may know, initial conditions of the universe that evolve until what we see today, which is the large-scale structure traced by galaxies, for example, the ones in the DESI survey, as you can see in the picture. So the summary of these observations, basically what we have learned, and we built this precise and accurate cosmological model, basically tell us that what we observed is described by the Lagrangian universe. As I was mentioning, have the comparison observations for CMD and LSS. And what we have learned so far is that this model, this Lagrangian model, is data-driven because of this reason, right? We have observations that trace almost the whole time, the whole age of the universe, and we use those data to constrain 3 parameters of this model, okay? And because of the amount of data we have generated by these observations is high precise. But yeah, another advantage of this model is that the interpretation is very easy to do because you can only few parameters, which are the cosmological parameters. And this basically leads to this constraint that teaches about what the universe is made of. So here it is, yes. Which is the summary of almost 70% dark energy, 25% dark matter, and the rest in the form of baryons. But it's not only that. Later observations have shown more mysterious facts about the universe. This is conclusions by DESI survey, the first data release mainly, basically tell us that at a very late time, seems like dark energy is changing, okay? And that's one of the most puzzling results we have obtained so far, is basically a parameterized equation of states for dark energy change. Okay. That's basically the first disagreement I want to show in this part of my talk, is that even though we have this precise model, there's still unanswered questions, okay? And that's basically the whole effort we want to do to solve it. Some alternatives to answer this is, what else is beyond Lagrangian, right? So there's an option of physics beyond Lagrangian we still don't know, we need to find. There appears to be tension between measurements of the early universe, CMB, observations, and the late universe, galaxies from DESI, for example. So maybe the answer to this disagreement may come from there, right? Oh yeah, what does it imply that dark energy is dynamical, right? It's not anymore a constant. The cosmological constant is not driven dark energy anymore, so we need to find that answer as well, right? And that's what we're trying to do for the next couple of years. Not only that, as in the last decade, a rise by the huge amount of effort provided by a service like DES, HSC, and KITS, there's this apparent tension in one of the parameters. This is called S8 tension, not to be confused with the H0 tension, which is completely different source. But for S8, there's supposed to be a tension as well, mainly driven by the comparison between observations of Planck, which provide an S8 of 0.84, compared to measurements of KITS. So this is the first release of KITS. It's not KITS Legacy that came out this year, that I'm going to try to cover later. But that disagreement seems to be this mild tension of between 1 and 2 sigma. So if you ask a mathematician or statistician, they will tell you, oh, that's not a tension, which I agree completely. But there's still supposed to be some disagreement fundamentally in the sense of what the information on the CMB compared to galaxies is given. Yes?
What is this parameter?
That's a very nice question, yes. So for non-cosmologists, S8 is a combination of this sigma 8 and this omega matter in this fashion, right? You have a square root. Basically, what you're trying to do, well, omega matter tells you the amount of matter in the universe, right? And sigma 8 is just a parameterization that you use from the primordial power spectrum to basically linearize it. So you have linear theory that basically describe the last case factor, for example. S8 is just a parameter that normalizes the amplitude of that power spectrum, okay? When you combine them, you're supposed to break the relations between these two, right? Because the way you try to infer these parameters is just by counting galaxies, right? Or counting the clustering of galaxies. So because these parameters give you the same information at the end, and the way you observe them, you need a way to break the degeneracy. Even more if you apply weak lensing, which I'm going to introduce later, okay? So we use this S8 to quantify both the amount of matter and the amplitude of the fluctuations. Yeah. And what is observed by these two experiments is basically this. CMB, as I mentioned, this slightly higher S8, and HSC, DES, and KITS, they both agree on a smaller S8. Maybe this one is kind of like outlier, but it's in the middle, right? But still, there's supposed to be this fundamental difference between these measurements. So cosmologists start asking, okay, where's this come from, right? It could be systematics, could be just the statistics, or could be something more fundamental, right? Something that is different between measurements of the early universe and late universe. Then you start talking about scales. This is all based on 2-point statistics, power spectrum, 2-point correlation function. So you need to quantify these measurements as function of the scale, the modes that you measure in the universe. So it could be that the difference comes as well from the different regime you're observing, okay? Yeah, the impact of gravity in the evolution of the universe. As late-time universe observes a model that is highly evolved by gravity, it is primarily different to what you observe from CMB. So also the difference comes from that, right? Or as always, the answer could be physics beyond that. Yeah, okay, primarily by gravity. So from the measurements I show, HSC, DES, KITS, they all infer these parameters using an approach with the weak lensing, okay? So to understand weak lensing as formalism, basically what you're trying to infer is the amount of matter in the universe by measuring the way that the shape of galaxies that you observe are distorted by gravity, okay? So you have a survey like HSC. So here there are you count galaxies as function of redshift, okay? So these are your sources, okay? So you observe mainly the shape of those galaxies that are usually elliptical or spirals, and you measure how much distortion you observe by all the matter between the source and the observer, okay? So at the end you observe something in 2D, right? And basically what you can do is by using the weak lensing formalism to study the amount of distortion in 2 components. One is the shear, which is this tangential stretching. Basically the shape is stretched. And the other one is the convergence, which magnifies the sizes, okay? So these are two fields that are, of course, connected, but this is what you use statistically to measure the amount of matter in the universe, for example. Okay. So yeah, this is how it works. You have sources that are in the background, and if you put matter in the middle, like the matter from that's the structure, well, you're going to observe galaxies that are more distorted as they get closer to a massive center, right? And this is what you're trying to measure statistically. So in terms of the sources, you have many options, right? As I mentioned, we've been doing this for last decade at least. So all these surveys started in the 2010s. You have KITS, DES, and HSC.
So I never heard about kids. What was kids?
KITS is the kilo degree survey. So it's 1,000 square degrees in the sky.
Smallish.
Smallish than DES, for example, yes. But bigger than HSC. Well, it's comparable, actually. You have some of the important hyperparameters information here. So KITS, DES, and HSC, they measure roughly 10 or 15. Well, HSC is kind of like, I'm just going to go there. But yeah, KITS, DES, they measure around 10 galaxies per Arc minute, okay? And yeah, they cover an area of between 1,000 and 5,000 square degrees, okay? Those measurements are going to give you very accurate results in terms of the sales. And that's basically the purpose of this service, okay?
So it doesn't go too much in depth, I guess.
Yeah, exactly. Yeah. They are big telescopes, of course. But yeah, what you want to solve is the amount of matter between redshift 0 and 1, right? So yeah, it doesn't need to go very deep in terms of the clustering, right? For Subaru HSC, it's a bit different. Yes, it goes deeper. So you have double number of galaxies now, right? So you can go even further in redshift as well. But with the price you have to pay is survey this small area. So this is the whole wide survey of HSC. In the end, year 6, I think, it covers around 1,000 square degrees. So it's a bit smaller than what it was initially planned. But still, of course, the information that provides, because this measurement gets more precise as you have more galaxies, is different to the one you expect from KITS and DES. So that's the reason why HSC is special, okay? And what is more important, that the signal-to-noise ratio of HSC is actually comparable to what you would expect for stage 4 surveys. So what are stage 4 surveys? Basically, the continuation of this work for this decade and the next. Okay. So we have Euclid, that is already launched, Rubin, LSST, that start to observe already, and Roma, which is probably for the future, but who knows, it's going to be launched because politics. But by the end of the day, yes, you start measuring more galaxies in a survey, in a bigger area. Okay? So your measurements are going to get more accurate and more precise. Yes, so as a summary for HSC, and I'm going to tell you a story of how this happened. It was in 2023, yes, in April. So we were in this conference in Kyoto. Basically, they unblind the results of HSC at year 3 that show fully consistency with previous results of HSC and also KITS and DES, which is the flow in the middle. Okay. So yeah, this is based on these studies that basically studied two-point functions, in this case, a power spectrum for different scales. So the different panels have different redshift pins because it's a tomographic analysis, so you can reconstruct the scale structure. But yeah, this is two-point analysis, meaning that you only restrict this to what the power spectrum and the two-point correlation function tell you. And yes, I was mentioning this is consistent with KITS and DES. And yeah, it showed this 1 sigma mild discrepancy with Planck, which is this difference you can see here. HSC is the yellow one. Planck is this narrow, very elliptical contour, which is the way the CMB constrains megamatter, basically. And yeah, there was this discrepancy. At the same time, and in the same conference, the conference was a CMB LSS conference, so we invite a lot of CMB experts. They were unblinding the results from ACT telescope, the Atacama Cosmological telescope, year 6, at the same time. Okay, so we had this very neat comparison. As you can imagine, ACT results were fully consistent with Planck, also showing this mild discrepancy with galaxy surveys. Okay, so of course, the whole conference was trying to figure out what's going on. And it was a very fun conference. We spent the whole week throwing ideas, looking at simulations, seeing things we haven't account before, and of course we gather some knowledge of what might be part of the discrepancy, and of course my talk is directed to that. What I can tell you is this analysis was done for this scale in the multiples. Okay, you have the galaxies in the sky, you trace them in a map, for example, and you model this using spherical harmonics. So you can model this in multiples. It's an angular scale to a minor resolution, which is very, very powerful. But what is important to mention is that even though at these scales, and this is something that is shown in the plots, this model lacks small scales analysis. What do I mean by that? If you look at the left-hand side plot, these multiple subpanels, you see this gray area here, basically at the small scales, the higher, okay? So these areas are discarded because you cannot model them with theory, okay? Small scales, you have the problem that matter evolves non-linearly, right? So you want to model that with a power spectrum. Your power spectrum doesn't reach those scales because there's a lot of astrophysics happening in there, right? So at the end of the day, what you want to do is to be sure your model is right, so you can get the cosmology right. So what you do, you just cut those scales, okay? Yes.
So when you say key, yes,
Yes.
Only large scale structure, not combined with anything else.
Not combined, yes. I think for this plot, I hope they didn't combine things. I don't think so. It's just galaxies, yes.
Plus, what linear perturbation theory, I mean.
So your model is usually based on linear perturbation field, yes. But yeah, if you ask an observer, they basically will ask, what the hell, why are you not using those data points? It took us years to get those data points right. So why are you not using them? Sadly, we don't have a theory for that yet. So yeah, it just has to be discarded. If not, they're going to apply a theory analysis. Yes.
And what are the limiting factors for pushing to lower balance?
Yes, okay.
Like less than 300?
Yeah, you're basically adding parameters, like varying parameters that are important in those scales. So if you kind of marginalize over those, they're going to basically move your constraints and they're going to make your constraints wider and so on, right? So you don't want to deal with those at these scales. But it's an important question because we need to find a way to deal with those, okay? So yeah, that's basically the point of this work, like how we deal with the small scale information. Okay? First, we need to understand what are the limitations of the two-point statistics. Okay? Power spectrum, for example. So here you have a bunch of realization of Gaussian maps. These are convergent maps. So they trace the large scale structure. And as you can see here, they're all Gaussian but one, which is made from simulations. And of course, if you have good eye, you notice they're different, but yeah, right. The problem is that if you calculate the power spectrum for all these maps, what you will see will be something like this. Okay, you have CL as function of the multiple. They're all the same, basically. Okay, there's noise there, of course, but all the maps have the same power spectrum. Okay, so you know that cosmologically you are losing information, or in other words, the two-point statistics is limited to what a Gaussian field can tell. Okay, and that's very important. But you don't have to stop there, of course. You can go to another statistics. So in this case, you do the count of pixels. And you notice that, of course, there is one map that's different. That is the one that comes from simulation. And as you can see here, is strictly non-Gaussian in the sense that it's skewed to the right, to the high kappa, sorry. Meaning that, okay, we need a statistic that captures the skewness, okay, that captures the non-Gaussian information. And that's basically the whole point of what we want to do as a planner. How do we get from HSC survey? How do we get from information on the power spectrum, which is Gaussian, to the higher order statistics? Okay, so that's what we did. This is the, of course, as you can imagine, is the HSC non-Gaussian statistics team that there are a bunch of collaborators from everywhere in the world. That basically we took data, we used the HSC Year 1 data because simulations were suited better for that data release. They were public, of course, so better for us. They cover more than 100 square degrees. So, of course, we need to update this for year 3 and year 6 in due time. We want to define statistics. In this case, for kappa maps. There's no special reason for that because in the simulation approach, this is easier to do. But of course, you can do this with gamma, the shear as well. Yeah. And this is a picture of the HSC fields. As you can see, this is divided in 6 smaller fields. They're all white in the sense that they all provide information that we're going to use. And you can see there's a mask as well. So what we're going to do is to try to use a different approach that replicate these maps to try to calculate statistics. So this is where I go to simulations because, yes, the base for how the statistics is using simulations. So simulations are great. I have to tell you that because I do simulations. You may know because you see them and they look very cool, right? You can always hear like these nice plots that people like. And of course, they also tell you a lot of physics of the large scale structure, mostly at the late times. So in terms of what you're trying to measure, yes, is how nonlinear the large scale structure evolves due to gravity at late times, okay? And that's what you measure. So this is a comparison of, for example, when you try to measure the LEO or the relative space distortions, what would it look like for simulations in comparison to the data? And they match perfectly, okay? So here you have formation component simulations, which are the lines basically. You have data, which is the rectangles in the background. And you also have theory. Well, there are different models here, so I'm just going to mean those. But what you need to know is that for theory, it gets more difficult to predict this, as I was saying, because this is not linear regime where the theory diverges from what you see in the data, because theory doesn't allow you to solve these small scales. Okay. Simulations match perfectly, meaning that with simulations, you can actually model what's going on there in terms of gravity, right? So in terms of what we're doing at the end of the day is try to recreate the universe, to map the universe using simulations, right? They have their limitations, of course, they're not perfect, because, for example, you can only sample a finite size, a finite volume for the universe, so you're going to miss fundamental modes that are not there, right? But we don't know because we have only one universe, so at the same time, simulations are better because you can simulate the same universe once and once again, right? What we know is that, of course, they're compatible in terms of the initial conditions of the CMB, meaning that you can generate always a Gaussian field that evolves like this in late times, okay? You only need to understand a bit about the gravitational collapse and how it goes with time using a background cosmology, in this case, cos lambda CDM. But yeah, at the end of the day, you generate this very non-Gaussian field. And in terms of details, of course, this is an example from Millennium TMD simulations, which are the state of the art in terms of all the ingredients you can include. You can use solve this for dark matter. You can input gas to solve baryons. You generate like stars information. So you go to very small scales, and they'll be shown to be very precise in that sense. They're great. And we're going to use those to try to understand a bit what happens in this nonlinear regime to see if the information from non-Gaussian statistics helps to these problems we have right now in cosmology. In terms of the statistical exercise, instead of theory, because most of the non-Gaussian statistics lack a theory description behind, so you cannot do inference in the level in the sense of Bayesian inference. But you can get something very similar, okay? So you start from some data, which, for example, is CSS or MIDX, that's a typo. So you start from a galaxy survey, for example, distribution of galaxies. As you can see, they trace the large scale structure, right? And you want to model that. And of course, we're going to use simulations to model that instead of full theory, right? We use the simulations, of course, not just for the model, but also to do validation, meaning that we can actually simulate what we're observing, calibrate to fit some of the parameters, and at the end of the day, what we're going to do is to emulate the theory with the simulations, okay? You need to define some statistics. Of course, at this time, people is trying to move to field level, meaning that they want to recreate galaxies point by point. But at the same time, you can do some other statistics, meaning that you compress all this information in a, for example, using the power spectrum, so you have less data you need to resolve, maybe in the dimensions, I mean. So your model needs to replicate this, right? You have two options, and I've done this because I usually try both. Basically, you need to understand the probability of the observation given a theory. For example, how well lambda CDM fits the power spectrum. Or you need to understand the probability of multiple theories, like for example, if you change the number of parameters, that the theory fits the data. Okay, that's basically frequentist versus Bayesian approach. Okay, you create a likelihood for both, of course, for both methods. And at the end of the day, what you're doing is test the theory with the observations, or understand the probability of the theory. So for this exercise, we're doing the latter. Okay, I'm trying to understand in terms of parameters how well they fit these observations. Okay, at one degree of probability, which is more a Bayesian approach. In terms of what we did, what we calculate is calculate a bunch of non-Gaussian statistics using these HSC maps. This is an example given in Gabriela Marquez's paper. You maybe know her. She's in Rio de Janeiro. And basically, she did this analysis using peaks and minima statistics. So here what you have is basically, you measure the number of peaks and minima as a function of kappa. This is signal to noise means that kappa is divided by standard deviation of the maps, meaning that you center everything at 0 and you move in distance of standard deviation. Peaks, of course, trace the high kappa values, so right, and minima to the left, the low values of kappa. You can do this analysis as function of redshift. But what's more important, you need to do this analysis as function of the cosmological parameters. In this case, SA, because it's the one we need to understand in terms of tension, right? So you model the statistics using simulations, how the statistics look for different cosmologies. And I don't know if you can see it, but in the background, you see different colors. So basically, how for different values state the statistic changes. Okay? We do the same for the CF, the 2-point statistics. Because the information that peaks and minima provide in this case is complementary to a power spectrum, okay? This usually provides just the amplitude of the measurements. If you need to understand the clustering, which gives you most of the information, you need to add power spectrum information.
So, Joaquin,
Yes.
It's easy to see why the CLs are cautiously segmented because the amplitude overall and be that, right?
Yep.
But the statistics of the peaks, it's a bit confusing. I would think that if you have greater amplitude in the clustering, then you would actually segregate more, not less the maximum and minimum.
Right.
But
Okay.
it appears that they got
No, they were
stronger, closer to 0. I don't know.
Yeah.
It's the other way around. How should I look at this? What is the intuition here?
There's an intuition. Well, what I haven't with this picture doesn't show is that we include several smoothing scales, right? So we have a map of kappa, just model at different resolutions, right? So 2 hour minutes, you go to 4 hour minutes, and so on. So maybe it has that included. But yeah, I think I see what you mean, like in terms of.
I would expect
Small,
more
exactly.
high and more low counts if
Yeah.
the amplitude of the clustering is larger, but
Mhm.
maybe it's a question of normalization. I don't know, but
It might be, but yeah, as you say, it's flipped in terms of comparison to power spectrum, right? So yeah, it's kind of like non-intuitive in that sense. It's true. And it shows the same for minima, so it doesn't depend on that. Yeah, so there I might ask myself too, yes. I think I have an answer for you right now. But yeah, this is basically what the model tells you, right, in terms of the statistics. And you have the data points as well there. Basically, those are the ones you're going to use to constrain the cosmological parameters. Okay. What we actually also do here is to mitigate some of the important systematics. I was saying that for small scales, astrophysics becomes important, like the effect of variance, for example, the effect of the photosynthesis, and so on. So we will try to mitigate over those effects to see the actual impact of your final inference. This is a forward model in that we push everything in our simulations. We create an emulator for the data test, and we use all these ingredients of the inference. Okay. What we need now is to define a likelihood to do the statistics. So this is the full pipeline. Yes.
So can you go back a little bit then?
Yeah, of course.
When you get, for example, the CLs of the converted to the SAIFR,
Mhm.
what is the the scale that defines your large scales from your map, right?
Right.
So I assume that you have to have the maximum level that is allowed by the map of the.
Of course.
Yeah. Does that match the one of the simulation? You have to do the simulations every time?
Yeah. So I just see if our maps, right?
You can feed it.
Exactly. Simulation. So with one simulation, you can fit the HSC footprint many times. Right?
So then, following that question, how does this non-Gaussian statistic of the distribution function captures the effect of large scales?
Right. Oh, that's an important question. So for large scales, you know that everything agrees with a Gaussian field, right? So you kind of assume that the information given by the non-Gaussian statistics at large scales will be the same given by CL, for example, a Gaussian, right? So it's not that we don't care about those. We trust that by posting the CLs there, you capture all the information about those scales.
I see. So, for example, any theoretical effect that you could have at a large scale that could appear in the simulations, you will not see it in the non-Gaussian.
For these statistics, no. Yes. If you use a bispectrum with very large aperture of the triangles, maybe, yes. But we don't go to that level yet. Yeah. But yeah, for bigs and minima, it shouldn't be that relevant. We have a paper that we're studying that, like with the size of the simulation we use.
Right.
We haven't found anything like more than 1%, so it's really small if there is anything for these statistics again. So this is the whole pipeline. It's very long. I don't want you to focus on it because it's too much information. I'm going to break it down. What is important here to say is that, yes, these are the statistics we studied for this data set. It's a year 1 so far. We're now moving the analysis to year 3, so probably if we have more statistics, they're going to go there. But these are summarized as the peak counts led by Gabriela, PDF, which was led by the other field. I did the analysis from cosmic functionals, scatter transform, which is led by Chen, and mark power spectrum, which is a new statistic that we defined with Jess Cowell, Helena ActiveView. But yeah, please don't focus there in the pipeline. I'm going to try to break it up here in terms of what simulations we use and so on, and all the other effects that we try to add. So in terms of simulations, you need two sort of simulations. One is the fiducial set. Basically is described here. This is based on the famous Takahashi simulations that are used for the HSC analysis. They're basically 108 full sky lensing simulations, so the ray trace. We're using the HSC number of galaxies, for example. As I mentioned, you can cover multiple areas with the HSC footprint, and because the simulations are full sky, you can fit them many times. So at the end of the day, you end up with 2,268 quasi-independent mocks that you use mainly to study the covariance, how the uncertainties in terms of sample variance or shown noise for your statistics gonna be resolved. We use another suite to do the modeling of the cosmology. So this is a sort of 100 simulations that change omega Mandel state in this way. So you have a range of parameters that you're gonna use your simulations to run. And then once you measure the statistics that you're going to use, you train an emulator to interpolate what happens in the whole parameter space. Okay. So basically what you need is to use this statistic, run it 100 times. And then by using some, for example, Gaussian process, what you can do is to infer what happens for all the parameter space for say any math. Okay. At this time is when you need to input the mass of the survey, for example, and see what happens for each statistic independent. So maybe there we study like Rao's question, like how this differs from different essays for the peaks, for example. But of course, it depends on the statistics. So it might be different for the cosmic functionals, maybe different for the power spectrum and so on. So, that is when you need to study that basically and understand. We didn't stop there. We tried to model some of the systematics. What can impact the small scales? People will always refer that variance, meaning that how's your feedback model for small scales impacting your statistics, and that's something that we studied. We study also intrinsic elements, meaning that the shape of galaxies is not only distorted by lensing, is also distorted by tidal fields of the large-scale structure that have an impact on the shape of galaxies. We studied as well. We start shape noise, meaning that how much a miscalibration would impact on this, and also photosis. Okay. Yeah, what happens if you change the way you measure photosis, for example, to bigger information in tomographic analysis. For observables, yeah, as I mentioned, we limit this to convergence that we reconstruct by measuring the shear first. Okay, meaning that you're going to go over a KS inversion, but the information is conserved. Okay, and you end up with the kappa maps like the ones I showed for the HC, and now you have them for simulations for each of the cosmologies and so on. What else you need? You need to calculate the covariance for any other statistics. So this is covariance. It doesn't matter too much here because what we do, it's not here. What we do at the end of the day is compress the covariance in terms of, we know the statistics we need to solve depends only on S8 number of matter. So by using what is called linear compression, you can go from a covariance of very high dimensions, these dimensions of terms of the beams of your CLs, your peaks, and your minima, to basically a dimension 2. Okay, the parameters you're trying to refer. I'm going to try to expand on that. In terms of the systematics mitigation, this is everything I mentioned, like everything we use to model the variance, model the intrinsic alignments, and all the other effects. Okay, so basically this is going to tell us which scales are valid in terms of the statistics. Okay, this is a paper study by Daniela Grandon that she changes the value models, seeing if any of these different models have a higher effect on the statistics. In summary, the answer is not really, not so much for the scales we use. Okay, so again, for the scales we use, it seems that systematics are not important than more than 0.3 sigma, meaning that in terms of S8, meaning that you're not going to shift your posterior too much if you add any of these systematics. Okay, here, for example, it seems like the most important one is photosis, which again, I'll try to come back to that later. But yes, a smaller shift that is probably not significant in terms of the error bars of the contours. Yes, so this is the summary of the study of variance. So when you add variance in your kappa maps, for example, it will look like this. So a residual basically shows that variance actually, because of the effective particle displacement caused by feedback, for example, you're going to measure slightly different kappa. Okay, I don't have the color bar here, which is a mistake for me. But yeah, this effect is really small in terms of the value of kappa. Okay, but the effect is there, which is funny. It's something you need to resolve, right? But if you measure the power spectrum again for those scales, so you have CL here for the hydro simulation, the one with variance divided by dark matter. This is really small. It's between 1% and 2% for these scales, the CLs, for this redshift. But again, in the CL is fine. For PDF, again, really small in terms of percentage. Because important for high kappa, but this green line is high NG model, meaning that it actually counts for more than what you observe with a fiducial model, for example. So in the more extreme case, the effect is not higher than 3% in power spectrum. Okay, so we were happy with that in terms of the scales we're observing, which are probably focused on between 300 actually and 1500, which is around here. Okay, so that's basically the way we understand the variance in our simulations. Yes, in terms of the livelihood and data compression, we start from the statistics. And as I mentioned, the statistic grows in number of beams very easily because you combine CLs, you combine the Gaussian, the size of the data vector, the number of small scales used, and because it's tomographic analysis, the number of redshift beams. So you can easily grow from 10 beams if you use one measurement to hundreds of beams if you start to combine things. Okay, so that will generate a huge covariance that if you only have a limited number of simulations, it's going to be limited in the sense of what the covariance is taking. So use the wrong covariance, your contours are going to be wrong. Okay, so you need to simulate that in a proper way. So the way we deal with that is basically using linear compression. which is called moped. Okay. Linear compression is easy to understand in the sense that you have a data vector here. As we have the dependency with the cosmological parameters, you need to take the derivative, and you multiply by the covariance, okay? So at the end of the day, these two have the same dimension, right? And because of this dot product, you end up with a dimension equals to the number of parameters you choose. So you go from 100 pins to 2 pins, okay? You may say, okay, what happened to the other pins, right? Are they lost? So it's been shown that moped, by if you use only a small number of parameters, will conserve the amount of information, meaning that it doesn't matter the length of your data. Then if you use the compression in the right way, the information will be conserved, okay? And that's basically the advantage of moped. It's not the only model you can use for compression. You can use different methods. But moped is easier in the sense that it's just linear, okay? You know it's linear, so it's just linear algebra in the sense, and you know the conservation will be, the information will be conserved, so you can define it.
Okay, just a general question about moped. I don't think I asked this before to one of these guys there, but does it conserve information in the Gaussian limit or the data vector? Your data vector isn't really Gaussian, right? So there's a kind of a.
It's a very important question, yes. The claim is, yeah, for Gaussian data vectors, the information is conserved. So then the question is, for a non-Gaussian lighting, for example, how much is conserved, right? I think the claim is that for roughly in the tens of parameters it is, right? Maybe if you increase the number of parameters to a higher number, yeah, it won't be the case. I think for the case we're dealing here with 2 parameters only, it's easy to show that it will be conserved. But basically what you're doing with this compression is to ensure that your likelihood follows erosion, okay? So you can use this theorem, for example. And this is just an application of the central ring theorem, right? So yeah, in that sense, you basically make sure that your likelihood is Gaussian, okay? It's not the other approach. You can do this with neural networks, machine learning. And there's also other methods like extension to model and so on. But yeah, at the end of the day, you want to estimate the posteriors, okay? And I've seen I cover a lot of times, so I just want to jump to the results. This is again all the statistics I'm going to show. So here's a summary of peaks and minima by Gabriela, PDF by Leander, and scattering transform by Xiao Cheng. Basically what they show, and I'm going to let you look at this for a minute, is that all the non-Gaussian statistics, for example, PDF, PDF is the blue line here, comparison to CLs only, they show a higher rate, okay? And if you combine, it's kind of like in the middle, right? Same with peaks and minima. In terms of the rate, seems like the non-Gaussian statistics also prefer a higher rate. Same for scattering transform, okay? Yeah, here. So even more, this paper by Xiao, it shows that the CL combined with the scattering transform actually agrees with that. Well, even for him, well, the way you define scattering transform is kind of alternative to power spectrum in the sense that you only change the basis. Instead of spherical harmonics, you have these different coefficients. He shows that the CL measured by the scattering transform actually agrees with Planck. So again, it seems like if you capture this non-Gaussian information, you prefer higher, let's say.
Sorry, the scattering transform is still just a 2-point statistics.
No.
No.
Depends on how many coefficients you use for the basis of your field, okay? These coefficients capture non-Gaussian information. The way you have to think a scattering transform is to divide, instead of a spherical harmonics, which is kind of like delta Dirac in Fourier space, you have this wavelet. So it's not only one mode you are analyzing, it's a combination of modes that captures non-Gaussian information.
Okay.
Even more if you use the nonlinear region. Yep. So it is non-Gaussian. Same for the other statistics. And again, higher rate. So it seems to be, well, the CL is consistent with the one by efficient analysis, for example, Ikage, 2019. It's consistent with the CL we measure. It's just that for us, the non-Gaussian statistics measures this higher rate. Minkowski functionals, which is the paper I left. Minkowski functionals is just different approach to mathematically understand these patterns generated by convergence maps. Okay? So Minkowski functionals define three functionals. In case of a 2D field, use this mathematical theorem. These three are related to geometrical properties of the field. So B0 is the area, B1 is the length, which goes with the perimeter of the kappa features, and genus, B2, measure this relation between the number of islands, the thresholds of white color here, and the holes which are in the kappa map in terms thresholded by kappa values. Okay. So this information can be predicted for a Gaussian field. It's a nice paper that basically tells you how Minkowski functions look like for a Gaussian field. You can do the derivation of a non-Gaussian field for a small perturbation that's called, which can be done by a large resolution in the sense of 10 minutes, for example. So you deviate from a Gaussian in that scale. But what is been shown that for the non-Gaussian case, it contains more information than the power spectrum only, as I mentioned before. And this can be seen in these plots, which are the Minkowski function, B0, B1, B2, it's a function of kappa. Okay. The comparison in the bottom panels is the comparison to a Gaussian case. Okay. So you can calculate this for Gaussian and non-Gaussian case, like kappa, and you show that these deviations correspond to the non-Gaussian features that you can quantify for these maps. And they usually depends on only the skewness and for high order the kurtosis of the field. So those are high order moments of the field. Okay. So you know for sure that you're looking at non-Gaussian information. And for Minkowski functions, you can imagine it's very similar results in terms of for individual Minkowski functions, B0, B1, B2, yeah, you show that they all prefer higher say in comparison to power spectrum. So yeah, here's the 2D contour. In terms of the SA contours, it's slightly higher for the combination of Minkowski functions and Minkowski functions alone. Okay. So again, they all agree in these higher sets. We didn't stop there. So this year, some people just came. Sorry, the year is wrong here. We were more optimistic probably when we start this project. But yeah, the paper is already out in the archive and already in review. So it's going to get official soon. But this is the Mark Power Spectrum study that basically trying to include the non-Gaussian features at the power spectrum level. Okay. So how do we do this? We use individual weights that basically enhance the non-Gaussian information in a nonlinear way. Okay. So how this is defined? Kappa, this is a mark, it's a function of kappa, that's why it's called Mark power spectrum. It's function of kappa. And they all focus in different regions of kappa. So for example, the blue line upweights what happens below kappa and downweights what for high kappa, similar to this cyan line. And the pink line, for example, is the other way around. So it answers what happened to high kappa. This has a very nice way to see it in the maps. So you have a kappa map here on the right-hand side. If you upweight it, for example, using the mark A, the blue one, you downweight high kappa. So all these islands that represent like high kappa values, once you smooth it, of course, are downweighted in terms of how they contribute to the power spectrum. So that was the one Jess studied. We have other studies using the similar features, but in a different way. I think, yeah, this one is linear kappa. This is MB. Yeah, this is the official. This is the one that defined first, actually. It's more easy to understand once you see these colors.
So these look like they are effectively filters, right?
Yes,
This is a fine filter.
They are.
Is this a magic filter for what?
What do you mean matching filter?
I mean, what drove the choice of those?
Perfect.
Those
Sure. Yeah, no.
I mean, why?
Really valid question.
Why that and not something else that I just draw?
Yeah. It's a nice question. In principle, it's fully arbitrary, right? And that's basically the sign one, MC. That's why it looks so funky, right? Like this pix is not physical, right? But the one we used first, the blue one, is optimized, meaning that you can find a function that maximizes information. And that's what Jess did in this paper. She basically defined a way that this mark gives you the more information from the non-Gaussian features. It's still not physically motivated, but you know that's optimal in the
So
sense
the
of
math says that they're optimized for the kinds of non-Gaussian features that you expect to see, because if you
Yes.
use a different simulation with different features, then you would find other. Okay.
yeah, 100%. Yes, yes, it's true. It's a bit arbitrary in that sense, but what you wanted to test is that if this function, once optimized, brings more information than power spec. The referee has a similar question, so we can probably discuss it. Yeah, nice one. But yeah, basically just found same story. I think the one I want you to focus, even though the improvement is, the shape is smaller, there's still a 40% improvement in terms of power spectrum alone, the pink one, right? You compare it with the blue one, I think there's a 40% improvement in the contours of the state. So that helps, okay? Basically, you end up with these smaller contours that make the model more accurate. We didn't stop there. This is kind of close to the end. We wonder what will happen if we change the approach, okay? Instead of doing this moped plus Gaussian likelihood, we said, okay, let's do something completely opposite. Let's change the way we compress the data and the way we do inference. In the way we build the simulations, we have enough information to train a neural network that will give you the right posterior. Okay, this is called a simulation-based inference that uses an implicit likelihood approach, so you don't need to define a likelihood. But the way you train your simulation, you basically try to learn the right posterior. Okay, meaning that you show the network many data from the simulations we have, and at the end of the day, you show the data, the real data, the C data to the same network already trained, and the network will tell you, okay, by what I know, this will be the posterior given that data. Okay, and it works in a very similar fashion, meaning that we have a bunch of statistics, we compress them now using a neural network, and we show that to them, to the different network, of course, the one that's estimating the posterior. And here is the results. This was led by Camila Novaes. She's also in Brazil. Basically, what she found that by neural compression, in terms of essays, the network predicts very well what the right essay will be once you train it with simulations. Okay, so it's identity line basically telling you for a given true essay that comes from simulations. Of course, you train your simulation without a data point, and then you try to predict it. Okay, it looks very one-to-one for essays. For omega matter, it seems like it's more difficult to predict, which is kind of expected because with convergence alone, it's very difficult to constrain omega matter. So we usually don't care about that too much. It's still important. But as you can see here, CL is definitely biased in terms of still the right. If you include non-Gaussian statistics, like the ones I show, it seems like it fixes this a bit for most of the omega matter were focused, right? It still seems to be outlier for some reason. Okay? In terms of the posteriors, same story. Higher essays once you combine non-Gaussian statistics. Okay, and it's kind of like the summary. Camila showed here that the one that with better improvements is in Cosmological, so points for me. But basically, again, what we show is that this higher essay in comparison to CL alone. Okay, so it seems like it's kind of like the end of the story for essay in the sense of one of the reasons to avoid this lower essay for galaxies is using the non-Gaussian information. Okay, and that's what we show that once you compare from CMB, like these cyan points here on top, and what's from galaxies here in yellow, seems like our data points that you see on Gaussian results are in the middle, which is convenient, because right. But it seems like this disagreement is disappearing once you do this non-Gaussian analysis. I don't want to finish there. I want to say where I plan to do in the future. We're in the era of Euclid and LST already, stage 4, it's happening. So of course, we need better simulations in the sense that now we need to simulate the LST area, which is 5,000 square degrees for the first year. But yeah, we also need to understand other sources of systematics, okay? It's a paper that led by Joaquin Armijo. It's submitted, it's already in the archive. But here we study the effect of intrinsic elements. So mentioning is also important. And we show that for some of the non-Gaussian statistics, for example, a PDF, we see like some of the models predict a very different PDF for a fiducial model, for example. So we want to study this in terms of different intrinsic element models, okay? This is the way that basically like the shape of the galaxies is shifted by tidal fields. So of course it depends on how you define the tidal field and so on. So we know for different models of the intrinsic elements, you have different, again, this is only possible because we use non-Gaussian statistics. If you use an ICTP power spectrum, it's probably the same, right? So it wouldn't matter. But because we're using non-Gaussian statistics now, we predict different results for different models. So the next step is try to infer those, include them, marginalize, and basically do the inference again, right? So we're doing a similar exercise with dynamic parameters. So that's basically how we increase the level of difficulty in terms of the inference, but this is all the level of MOS. So we're trying to do that now. So this is part of the LSST collaboration. So when the data is there, you're part of the LSST. And not just that, we are also extending to further than lambda CDM. We're doing a similar analysis for modified gravity. This is based on FFR model in scalar field modification to general relativity. But yeah, what is easy about this model depends only on one parameter, the force. That's basically what modifies gravity. And we have emulators for that, which is, again, a positive in the sense that we can do the same approach. We're doing this for HSE3, which is public already. This is how the data look like. We're just here, so I cannot show results yet. But again, we can use the same method to see if we can now constrain this force parameter. So this is the stage 4 prospect. So we're trying to aim to something of this value. The current constraints are given by usually analysis of 2-point statistics again. So we hope that the non-Gaussian statistics will help to, okay? But this is something that I'll probably show next time I give a talk. So, yeah.
So the sensitivity to modified gravity is to the sleep parameter, or how does it come in the observable theory?
So you have convergence maps created by modified gravity simulations, right? So you know they're not lambda CDM. So again, you test your statistics and see how they look like in comparison to the data. Yes, so this is a scale-dependent model, meaning that it also depends on the scales you're looking at. Yes. Yes. But yeah, I'll finish here. The summary is that non-Gaussian statistics seems to solve this, say, tension or discrepancy, however you want to call it. We forward modeled many of this. We improve constraints roughly 30–40% in comparison to power spectrum alone. But we always shift, say, to higher value, meaning that the tension is solved. It seems like even if we change the approach, results are the same, so that's positive. But again, this is going to be confirmed or reconfirmed by stage post survey. So stay tuned for that, and please ask any questions that you have. Thank you.
So I think.
Yeah, please.
Could you go back at the comparison of the different constraints and for different surveys of sigma? Let's say,
Is this whisker loaded up? Or sorry?
I don't know. Sorry.
This one? Is that okay?
Yes. Yes, I guess. So if I understand correctly, your main conclusion was that by using the non-Gaussian estimators for these,
Yes.
you're improving the constraints, or you're moving towards the real value of RGB. And this is due because the non-Gaussian structure of these parameters allows you to go to nonlinear scales.
Yes. So they provide also the
you short things. So my question is, so there is a lot of people that needs using nonlinear modeling also for the CLs, right?
Yes.
That's is pushing nonlinear scales.
Yes. Depends on what you use, but yes.
Right. I had the idea that I'm using also the same emulator, simulation-based emulator for some bits, right?
Right. Okay. Yes.
So I would expect that if you combine those emulators, the constraint should move to the same.
I mean, not really, because one of our claims is that CL only gives you Gaussian information, right? So it doesn't matter how further you push.
Right,
The only
usually
use-
if you go to higher and higher orders,
Yes,
you are capturing no Gaussian information in the two correlations, right?
but maybe not with the same accuracy that a non-Gaussian statistics will do, right? Because CL is defined for a Gaussian field, right?
Right,
So the information you're going to get back is going to be the one limited by a Gaussian field.
I see.
That's our claim, yes. So what you can do is use CL plus, nonlinear theory, right? But theory doesn't go there because even if you add more loops to your integral for the power spectrum, you are limited to the scales you can solve by a Gaussian field.
I see.
Yes.
And still the same claim here is because this difference is due to nonlinear.
Yes. It's not the only reason. Like people from kids, they came with this paper recently that they changed a bit the analysis of redshifts estimations. Not expert, that's why I cannot give you more details. But they basically solved the same tension of that as well. And now kids claim that, okay, we did it wrong before.
Right.
Now that we treat the redshifts right, even without Gaussian information, it's cosmological enough to solve this same tension. Yes.
Right, I see.
Yes.
So moving towards plan.
Yes.
Okay.
Yes.
And in, sorry, you want?
No, that was it.
Yeah, so my question there is that with this kind of pipeline, which you basically forward model everything, SPI and such.
Yep.
Is it capable of mimicking completely the attention before, in the sense that you can just take this forward pipeline, right, reproduce kits with, let's say, the bias redshifts and such, and have a prediction only from plan like the same side, and kits like because it would be great to like pinpoint exactly what point of the analysis bias the
Definitely. Yeah. So to do that, yes, you have to change the simulations you use, right? Like it would be nice to show that this approach is agnostic in terms of the simulations you use. Right? I think it's what people are trying to do now. Right? I mean, people is moving to SBI for that reason, because you need to understand that this is solved by any simulation of use, or it's just because we were lucky and we used the right simulations, right? It's probably not solved at this minute because people hasn't done it at that level of comparison, right? It's what we claim, right?
the claiming here concretely would be the problem is small scale non-linear baryonic effects on small scales that bias the analysis. S8.
Basically, the claim for 2-point surveys that have this smaller set is that the scales we use are give you all the cosmological information, right? And we get this say in comparison to plan, right? What we change is that okay, we're gonna include smaller scales. We're gonna add proper statistics that capture information of those scales, and we're gonna get these results for S8, right? We know that because of the mitigation analysis we did, that the variance are not going to shift those results, okay? Because the statistic is not that sensitive to variance as you might think, right? Maybe it's different from CS, right?
Yeah.
So in terms of baryonic parameters, the ones we studied, our statistic is not sensitive to those. So we know that we are not biased about that.
Yeah, so I guess it's connected to the question. Which is as you go to smaller scales, it's like you have a figure of bias and a variance, and that they are going in different ways, right? I mean, the CLs maybe are being more biased, but they also getting more variance, whereas the information from the non-Gaussian statistics are coming in and they are giving more information there, but in a way that they just simulate, they don't generate bias. So maybe there's a figure that shows this, that as a function of scale, you lose value with the CL and you gain value in the non-Gaussian. It's just that it's hard to see, right?
Of course, yes. It's hard to limit your power spectrum and say, okay, I'm going to stop here and say, this is linear scale, this is non-linear scale. Right? Quasi-linear regime.
But
so
why isn't it possible to make a figure of bias together with a figure of merit as a function of scale and show this explicitly, right?
I mean, I think you can do it with Fission analysis.
It will be,
but it's too conservative. I mean, it doesn't tell you the whole story because we think
no,
that
you can do figures of merit with any, if you have a PDF, you have figure of merit.
yeah, of course. But once you have to add all these parameters that you think are important, I think you're limited by the data you have, what you can use to model it.
But pretty much that's what's happening, right?
Yeah, I think so. So yeah, and variance are definitely a factor.
But then I might not, guess it's something that the point is that with this way of doing the analysis, I get it, you don't get the bias. But then the question is, where was originally the bias coming from?
Yeah.
And is that they were making not sufficiently conservative cuts in scales for PK, and then that was somehow leaking into the say posterior, or where?
Yeah, I mean, this is my view, right?
Okay.
But basically, what is causing this difference here, the way we show it here, is that for a two-point analysis, the scales you're looking at are not going to give you the whole picture of say. And we try to say that with non-Gaussian statistics, you have a better picture in comparison to that. That's why we shift.
And then
If that's right, who knows?
then maybe like nobody wants to say explicitly, maybe it's that
That's true.
yeah, this from kids, let's say, it was.
That's the other point. I only can deal with the systematic side. No,
Yes.
we control those at that level for the scales we look, right? Kit says now that if we change the systematic hypotheses, sees that also solves this situation. That's different reason, but it proves the same of yes. Thank you.
Great.
Any more questions?
But then that means if kids redo this
Yeah.
with your non-Gaussian statistic, they will have a more shift value.
Not necessarily, because again, that's for 2 point only. Maybe non-Gaussian is not sensitive to that, so it wouldn't change that. Yes.
But tighter.
Tighter, yes. So that's something the stage 4 will compare because of the area.
Anybody else? All right, so thank you, Joaquin. So systems.
No,
It's a verb, no?
That's space. We can use the opposites to work.
You know this, you don't know this verb, right? Testa. Testa big, Friday, so.
You will learn it now.
You learn
That,
it.
it's making that.
That's what I call it.
You're giving a bad example.
I mean, the guy just arrived, come on. Se vai ficar como é que Carlos? Então depois eu quero mesmo falar com você. Vamos. Pode ir. Não, pois não, eu também, eu tenho que sair antes de uma 4 da tarde, porque.
Não, a coisa minha não é simplesmente eu fui algumas
Depois eu falo. Bom, coisa. Bom. Fernando, você não quer dizer?
Okay, so I want to show you some things. I think it's a very implementary